Hey everybody, Dr. A here, and in this video we're going to be exploring another example of particle equilibrium. So let's go ahead and get started. In the given information, we're being asked to compute the required length of cable AC so that the 8 kilogram mass can be suspended as shown. So if we take a second and look at this two-dimensional figure, we have a cable AC here, and we have another cable AB here, and we have this 8 kilogram mass hanging vertically from point A. Now, we're also being told that the undeformed length of the spring in AB is 0.3 meters, okay? So basically what that means is undeformed, which means before we hang this mass at point A, we have the length of this segment AB is 0.3 meters. And we're also being told that the spring has a stiffness of 400 newtons per meter, okay? Now, the total horizontal length of the whole setup is 1.5 meters. So we see this dimension line extends horizontally from point C all the way over to point B, okay? Now, anytime we have a problem that involves a spring like we have in AB, you automatically need to think Hooke's law, okay? Hooke's law is basically a relationship that says that the force that develops in a spring is directly proportional to the amount that it will stretch. And it was developed by Robert Hooke. So we need to somehow get that in our mind. We're going to have to apply Hooke's law somehow into this problem. All right, so we put that in our back pocket for now. But to get started, what we really need to do is figure out what these forces are in each of these cables, AC and AB. And then we can relate the force in AB to the amount that this AB spring is going to stretch. And we'll eventually be able to piece together the solution to what we're being asked to solve for, okay? So let's go ahead and write solution. The first thing I'm going to do is I need to get the weight of that mass, right? It was given to us as 8 kilograms, but we sum forces, not masses. So we say 8 kilograms times 9.81 meters per second squared, and you should get a value of about 78.5 newtons. Remember, a kilogram times a meter per second squared gives you a newton, all right? So what do we do now? Well, now what we're going to do is draw a free body diagram of that particle A, all right? So that little connection or that, eye bolt, whatever it is, that ring at A is a particle, and this is a two-dimensional particle equilibrium problem. So we draw a free body diagram, and what do we have hanging vertically here? Well, that's just that 78.5 newtons. That's that weight. What do we have coming off to the right? Well, that's just going to be an FAB, okay? And then what else do we have in our free body diagram? Well, we're going to have this diagonal force here, FAC, okay? And that is going to be at that 30-degree angle. So I'm going to try to color coordinate here. We have that 30-degree angle there. And so at this step, we just apply our equilibrium equations. Remember, for a two-dimensional particle equilibrium problem, we've got two equilibrium equations. What are they? Well, one of them is sum of the forces in the y direction equals 0, and we call things pointing up positive. And if we were to look at this free body diagram and set up this equilibrium equation, what we're going to have is FAC times the sine of 30 degrees minus 78.5 newtons equals 0. And from this, we can directly solve for FAC. It's just one equation with one unknown at this point. So we can say FAC is going to be equal to about 157 newtons, okay? Now, what's our second equilibrium equation? Well, we have sum of the forces in the x direction equals 0. So we can apply this to solve for FAB. So the way we set this up is we're going to say 157 newtons, that's FAC over here, times the cosine of 30 degrees. Now, we can't forget to do what? What we need is a negative in front of that. Why is that? Well, FAC is pointing into quadrant 2, which has a negative x component, okay? So that's why we have a negative there. And then we're going to say plus FAB equals 0. So that's everything with a horizontal or x component. We'll do a little bit of rearranging and we'll get FAB is equal to about 136 newtons. Now, if this was kind of an introductory type of problem from like a few videos ago, that might be the end of the story, right? But we have to do more. We're being asked for more things here. Specifically, we were asked information about the required length of AC, and we know that we have a spring in AB. So again, think about what's happening physically. We hang this 8 kilogram mass from A, and then what happens is this spring wants to stretch, right? It tends to elongate horizontally, and that's where we have to use this idea of Hooke's law, okay? And so what does Hooke's law say? Well, let's write this out. We're going to say Hooke's law says that the force in a spring is equal to the spring stiffness times the amount of stretch. And so in words, it's like what I said a few minutes ago. The force developed in a spring is directly proportional to the amount that the spring stretches. And what is that constant of proportionality? Well, that's this spring stiffness K. So for our application in this problem, we'll say FAB equals KAB times the stretch of AB. So we can put these little subscripts of AB for each of these terms to indicate that, hey, we're concerned about what's happening here in AB, all right? And so what I'm going to do is I'm going to rearrange this, and I'm going to say that the stretch in AB is going to be equal to the force in AB divided by the stiffness of AB, okay? Now, when I package this together, do I have both of these values? Yeah, absolutely. I just solved for FAB over here. That was the 136 newtons. And then the stiffness AB was given in the problem statement, right? That was, we were told that that spring has a stiffness of 400 newtons per meter. What that really means when we think of stiffness, what that means is it would take 400 newtons of force to make that spring stretch 1 meter. That's kind of what that means. So we're going to say 400 newtons per meter. And if we do a little bit of rearranging here, what do we get? Let's punch this in our calculator, 136 divided by 400, and I get 0.34 meters. So what that means is that spring in segment AB is going to stretch or elongate by 0.34 meters, okay? And so that is the amount of stretch. That's how much it actually stretches. So what would be the stretched length, okay? So again, think about that question. We know how much it's going to stretch. So what is the new length of AB after it has been stretched? Well, that's where we have to incorporate this 0.3 meters in here. We were told that the undeformed length, which is the unstretched length of AB, is 0.3 meters. So all we have to do is we say that the length of stretch of AB, so I'm going to call that L sub S AB, the stretched length of AB is how you can say that, is going to be equal to that unstretched length, 0.3 meters that we were given, plus the amount it stretches, SAB, okay? And so when you put that together, you get about 0.64 meters, okay? So that's how much, that's the new length of AB after it has been stretched, okay? Now, we're almost done, all right? Let's go back to see what the problem was asking us for. It says, compute the required length of cable AC. So what we're looking at is this diagonal length that we're really interested in, AC, okay? So how do I relate all of this together with the length of AC? Well, I use this total horizontal length of 1.5 meters to help me do that. So here's how we can think of it. This total 1.5 length is going to be equal to what? Well, it's going to be equal to the horizontal component of AC plus this overall stretched length of AB, okay? Think about that one more time. 1.5 meters is equal to the horizontal component of AC plus the overall stretched length of AB. So I can label this LSAB, the stretched length of AB that I just calculated. Now I just need this, you could call this maybe X sub AC, which is the horizontal component of AC, okay? And we can piece it together and relate these dimension lines together. So how about I write that out here? How about I say 1.5 meters equals X sub AC plus L sub S of AB, all right? And so how do I build this out a little bit more? Well, we have 1.5 meters. What is the X component of AC? Well, that's just the length of AC times the cosine of 30 degrees. Basic trigonometry. We take the diagonal length, LAC, and we say times cosine of 30 degrees, and we'll get XAC, okay? And so that's how I'm relating XAC and basically substituting in LAC times cosine 30. And then we say plus that 0.64 meters that we just calculated. And now look what I can do. I can rearrange this and solve for LAC, okay? And because at this point I just have this one equation and I have just this one unknown. So I'm going to say 1.5 meters minus 0.64 meters, and then all of that divided by cosine of 30 degrees. And so I get about 0.99 meters. Okay, and that's my answer right there. My answer is 0.99 meters. So in practicality, you would say 1 meter, okay? But that's 0.99 meters is the official answer. And that concludes this example. So if you found this helpful, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.